So we are going to look at harmonic functions. I think we mentioned them a little bit in the previous. We mentioned them in the previous two short video clips. So the harmonic functions is defined in terms of what we call the Laplacian. The Laplacian is it's a partial differential operator where you take the first order and the second order partial derivative with respect to the real part, second order partial derivative with respect to the imaginary part, and then you add them up. So it operates on a function. So if you have a function, a complex valued function from a domain to which is twice differentiable, then the Laplacian on that the function is harmonic if the Laplacian is equals to 0. So the Laplacian has to be equal to 0 for the function to be harmonic. So let us go to a few things that we have. So if a function is analytic, the issue is that it will be infinitely differentiable. You can differentiate it as many times as you want. Here is a crucial result. It says that if a function on a domain D is analytic, then the real and imaginary parts are harmonic in D. So in analytic, there's a connection between analyticity and the function being harmonic. Those two things are connected. And because they are connected, the fact that it is analytic means that it satisfies the Cauchy-Riemann equations. And the fact that it is harmonic means that it will satisfy Laplace's equation. So if those two things are satisfied, we end up with a special relationship between the real part of a function and the imaginary part of a function. So if it is analytic, then U is going to be harmonic and V is harmonic. If it is analytic, then U is going to be harmonic and V is harmonic. So we have that. Then it means that if your function is analytic, there will be a connection between your U and V. It's not that if you have a U, it just has to have a matching pair, which will have special properties, and that matching pair is called the harmonic conjugate. So if we have U, it has a special function which will make it analytic. If we have V, it will have a special function V which will make analytic. These pairs are what we call conjugate, harmonic conjugate, or harmonic conjugates. So let's just look at an example of how to find this. So the example is this. You are given this function which is U e to the minus 3x cos 3y. Is this function harmonic? And if it is harmonic, find its conjugate. So what do we do? To show that it is harmonic, first we show that it satisfies Laplace's equation. So we differentiate twice. If you take this is just a differentiate twice with respect to x. The derivative is to evaluate in this case because they are separate functions. These functions are separated. So differentiate with respect to x, you get this. Again, you get that. 36 e to the minus 3x cos y. Differentiate with respect to u, you get this. And then when you do it again, you get minus 36. These two have different signs. So if you add them up, which is this, that's the Laplacian. If you add them up, they'll just add, they'll give you 0. So U is harmonic. If it is harmonic, now let us proceed to find its conjugate. So to obtain the harmonic conjugate, we should observe that the function is analytic. And if it's analytic, it should satisfy Cauchy-Riemann equations. Satisfy the Cauchy-Riemann equations. So the first Cauchy-Riemann equations equation, sorry, the first Cauchy-Riemann equation says du dx, which is this, should be equal to dv dy. Now, we take the right hand side, and it gives you, it is connected, this is connected u to v. So we want to find v. So if we take the right hand side, we have this. Then we integrate with respect to y. We integrate with respect to y. If we integrate this with respect to y, we'll get our harmonic function. Our harmonic function is v. The v is being equals to that. So v is this, and the hx is a constant of integration, because if you differentiate this with respect to y, and there is a function, is a pure function of x, that will become 0. So that's how this harmonic conjugate comes into play, and this constant of integration comes into play. So the first one is being satisfied, the Cauchy-Riemann equation. The second one states this. It states this du dy is equals to minus dv dx. Du di, we have it, it is there. So if you, this is going to be equals to dv dx. So we just use the v which we have just obtained to get dv dx. If you dv dx, then you are just differentiating the last one. It gives you this function, and you compare it to, and you can compare now your the dv dy and minus dv dx. If you compare the two, the only difference is that, and the only observation that you have is that this is going to be equal to 0. So the constant of the derivative of the constant of integration is going to be equal to 0, which means that our h of x is equals to k. Therefore, our v is equals to this. Now we have v. I think we can combine your u, the u which we originally had, plus the v which we now just obtained, and then it has a k there. I think this k is also multiplied by, it is also multiplied by I. So to get the function in terms of z, you just substitute y equals to 0, and that will give you this. And in this, if you go to the real part, if y is equals to 0, it means our complex number is now real. So you can just substitute where you have z, substitute it by, replace that x by z, then you have this. So this function is the this function here is the analytic function that we had. It is its components are harmonic. So that's how we use harmonic functions. How we use the Cauchy-Riemann equations to obtain harmonic conjugates. So let's stop there for today.